In this video, we're going to calculate atomic energy transitions. We're given the Bohr model of the hydrogen atom shown below. An electron transitions from n equal to 3 to n equal to 2. So n equal to 3 is the initial case, and n equal to 2 is the final case. We want to find A, was the photon emitted or absorbed? B, what is the difference in energy, delta E, in units of eV? So here we're given the Bohr model of the hydrogen atom. In the nucleus sits one proton of one positive electric charge. To make the hydrogen atom an element on the periodic table, it needs to be electrically neutral. So therefore, we must put one electron surrounding the nucleus, which has one negative electric charge. The electron could be located in the ground state, n equal to 1, the first excited state, n equal to 2, or the second excited state, n equal to 3. In this particular case, we're given that the electron starts out at n equal to 3 and transitions down to n equals to 2. And we want to find out, is the photon emitted or absorbed? Because the electron is going downhill, it's going towards the nucleus in that direction, the electron is going to give up energy. And so the electron will emit energy. So our first answer is going to be emitted. The answer to A is emitted. Think of the hydrogen atom Bohr model as an apartment building, and you are on the ground floor. If you wanted to climb the stairs and move upward to the first floor, you would need to eat food to gain energy and move upward. Same thing with an electron. It needs to eat a photon or absorb a photon and move upwards to go to the next level. It's easier to go downhill than it is uphill. So when you're going downhill, you emit, and when you go uphill, you absorb. You have to absorb first to move uphill. What is the energy difference in delta E in units of eV? Well, we have an equation. There's actually several equations that we could use. Delta E is equal to E final minus E initial, which is equal to minus 13.6 eV, parentheses 1 over F squared minus 1 over I squared. Delta E is equal to HC over lambda, and HC over lambda is equal to minus 13.6 eV, parentheses 1 over F squared minus 1 over I squared. Well, let's take a look at what we're given. We're given I, we're given F, and we want to solve for delta E. So the logical one that we want to choose is this first equation. Delta E is what we want, and we're given F and I. So we're going to use this equation. Delta E is equal to minus 13.6 eV, parentheses 1 over F squared minus 1 over I squared. So now that we selected our equation, we need to know some constants. Well, we put some here, but we don't need to know them for this particular equation. But we do have an electron volt conversion to joules, but the question does not ask for joules. It asks for units of eV, so we don't have to worry about that because our answer already has eV units in the equation. So let's take a look at the equation. Delta E is equal to minus 13.6 eV, parentheses 1 over F squared minus 1 over I squared. We carry the minus 13.6 eV down, and the final state is 2 squared. We end up in level 2, but we start out in level 3. So we just put in 2 for F, and we put in 3 for I, and now we need to calculate this out. 2 squared is 4, 3 squared is 9, so we have 1 divided by 4 minus 1 divided by 9. Let's start with that calculation first. We go to our Google calculator and we type in 1 divided by 4 equal to minus parentheses 1 divided by 9, close parentheses, equals. We have our answer, so we go back to our calculation. We did this part. Now we need to multiply by minus 13.6. We go back to our calculator. We multiply it by minus 13.6. And we hit equal sign, and we get a value of 1.888888. So we can look, and 88 is greater than 50, so that kicks this 8 into a 9, and our value is minus 1.89. EV is our answer. So we carry it down, minus 1.89 EV. Now remember, this is what the electron is giving up. And we want to find out what is the difference in energy in EV. So our answer, the electron is giving up minus 1.89 EV in energy. Now the negative sign is telling us that the electron is bound. The electron is bound. The electron didn't get released free. The electron went from n equal to 3 to n equal to 2. It is still being bound by the atom, and since in this direction, going towards the nucleus is negative, and the outward direction is positive, we do not have an electron that's being emitted freely from the system. So we have an electron that's transitioning downwards. It is still bound to the atom, and therefore we have a value of minus 1.89 EV. The electron is still bound, but it released 1.89 EV of energy.